Alright, so this is the last video in the similar figures topic, and that's on similar volume. Jokes in the name, this is going to be very similar to the previous video, but that's why this is actually quite a nice topic, because everything is kind of very similar. So to begin with, as an introduction, I've got a little example as to showing how we come about finding the volume scale factor. So to start off with, we can already see that it has a linear scale factor of 10, because every side I've just multiplied it by 10 to get that larger shape. So I'm going to find out the volume for each of these. And remember, volume of a cuboid is length times breadth times height. So that's going to be 3 times the 1 times the 2, which is just going to come out as 6. And here, it's going to be 30 times 10 times 20, and that will come out as 6,000. So what I'm going to do now, in a similar way to my area scale factor, I can find my volume scale factor using that same new over old, just using the volumes instead. So I'm going to make my larger shape my new one, and my smaller one my old. So that's going to be 6,000 divided by 6. And that's just going to come out to 1,000. So my volume scale factor in this question is 1,000. Now, if I compare my linear scale factor with my volume scale factor, my linear one was 10, my volume one is 1,000. In a similar way to my area scale factors, in that case, all I had to do was square. In this case, I'm cubing. 10 cubed is 1,000. So that is what I'm going to use for today's work. So volume scale factor is equal to the scale factor cubed. So let's take a look at questions using this. And in the same idea as my similar areas video, I've got 3 different types of questions. And what you should find is that it's basically the exact same idea. I'm processing things the exact same way. All I'm doing is using a volume scale factor instead. So let's jump straight to it. So this first one, the cuboids below are similar. Calculate the volume of the larger cuboid. So the larger one, that's going to be my new because it has my unknown. So that's my old. So to start off with, I need to find my linear scale factor because I don't have information on my volumes yet. So that's going to be the 35 over 25, which simplifies down to 7 over 5. So then my volume scale factor, I take my scale factor and I cube it. So I'm going to do 7 over 5 and I'm going to cube that. And that comes out to 343 over 125. So that means then my new volume, I take my volume scale factor and I multiply it by the old volume, that 175. And that gives me an answer of 480.2, and it'll be in centimeters cubed. And so another way to remember that you are cubing your scale factor is look at the units, centimeters cubed, or we could have meters cubed or millimeters cubed. And that sort of gives us a clue as to why we might cube our scale factor. All right, so next type of question. Are the following pairs of cylinders similar? So I've got 2 cylinders here. In a similar way as before, I'm going to call one of them my new one, and I'm just going to go for my larger one here and call the other one old. And I'm just going to ignore the volume on the new cylinder. I'm going to pretend it doesn't exist and process this all same as before. So my scale factor, doing my new over old, that's going to be 18 over 12, which simplifies down to 3 over 2. So then my volume scale factor is going to be that 3 over 2 cubed. And that's going to come out as 27 over 8. So then my new volume, I take my volume scale factor, multiply it with the old volume, which is at 300. Make sure you definitely pick the old one. And then that comes out as 1,012.5, and it'll be in milliliters. And one thing, don't get thrown off by the fact it is milliliters. Liquid volume units are also part of volume. So here we can see my answer has come out the same as what we were told the volume was. So that means they are similar. So in the same way as before, I need to write a little statement explaining why I know that is the case. So, using the linear scale factor from the shape gives the volume in the question so they are similar. So using the linear scale factor from the shapes gives the volume in the question, so they are similar. And that statement is really similar to what we wrote before, but all I've done literally is just I've swapped out the word area for the word volume. Okay, one last question to go. So this time we're told the following pyramids are similar. Calculate the height of the smaller pyramid. So here's where my unknown is. So that's my new, which makes this one my old. I can't do my linear scale factor because I don't have both of those pieces of information, but I can do my volume scale factor. So that's going to be the 56 over the 109.375. So I'm going to put it on my calculator for it to simplify a bit. So 56 over 109.375, and that comes to 64 over 125. So then to find out my linear scale factor, kind of similar as before, remember my linear scale factor cubed is my volume scale factor. So in order to get to just my linear one, opposite of cubing is cube rooting. So I want to cube root both sides. So I'm going to cube root that volume scale factor. So in my calculator, putting in the cube root of 64 over 125. So cube root of 64 over 125. And that comes out as 4 over 5. So then my new height, I take that scale factor and I multiply it by the old height. So 4 over 5 times by 30, and that is going to give me, that'll be 24, I believe. 24 centimeters. So let me just quickly double check. 4 over 5 times 30. 24, there we go. So that's how similar volume. So the idea, basically exact same as before. We've just got that one slight variation with getting to our volume scale factor. Let me know if you have any questions, and good luck with the work.